For A, it's asking for the difference quotient, which best approximates the rate of change of G. So we have these two things. The difference quotient, okay, is just essentially the slope of the secant line. So it's going to be a slope between 2 points on this graph. And the rate of change is given by the slope of the tangent line. Okay, now with that known, we want to find out the slope of the tangent line at 2.5. That's basically the slope of the tangent line at that point right there. This is 2.5. We want to find the slope of the tangent line, but that actually is exactly this line. That's the tangent line. Okay, so we're trying to find the slope essentially of this line, which is actually the slope of this line joining these 2 points. The slope of the line joining these 2 points is that, and that's the slope of the secant line. That is the difference quotient. So the difference quotient in this case, as always, is given by G of 3. Or which one is it that's going to best do it is going to be the, this between this point and this point. This point right here is 3 comma G of 3, or yeah, G comma G of 3. And then this point right here is 2 comma G of 2. And we know the Y values because they're clearly written here. G of 2 is just 4, and G of 3 is just 1. So now computing the difference quotient, or the slope of the secant line, this line right here, G of 3 minus G of 2 over the difference quotient, the 3 over 2, the quotient, 3 minus 2, the difference in the x's. And again, this is just the slope of the secant line, or the difference quotient. So G of 3 we found out is 1, right here is 1, minus G of 2 is 4, over 3 minus 2 is 1. I'm going to get negative 3. 1 minus 4 is 3, is negative 3, divided by 1 is 3. Part B, they're asking for the limit of h of x, but here I just rewrote how they defined h of x, which is g of f of x. Now to do this, you always want to keep in mind coming to 3 from the left and from the right and seeing how that works with f of x. So let's see what we have. We have a limit as x goes to 3, but from the left of g of f of x. And let's see what we get here. We're just going to do some analysis like freehand. So as I get closer and closer to 3 along f, but from the left, right? This is from the left of 3, right? So this is from the left for values less than 3. We can see that we're getting closer and closer to this value along y. Let's say, look, so this is like whatever, let's say 2.9. If you go up, right, I'm at maybe 2.5, and then if I go to, let's say, 2.99, right, I'm even closer to 2, but from above 2. So as I get closer and closer to 3 from the left, this f of x value is getting closer and closer to 2, but from above 2. So again, it's key to realize that this value is going, 2.1, that's above 2, and then it's getting, as I get closer and closer to 3 from the other side, it's going to go to 2.01, let's say, and then it could go to 2.001, and so forth and so forth. And I'm getting closer and closer to 2, but from above 2. And then if you look, as I get closer and closer to 2, because now this is now an x value, because it's inside G. So I go to G, I go to the graph of G, and these values right on the inside are approaching 2, but from above 2. So where's above 2 along x? It's over here, right? It's that region right there. So this is above 2. So this is like 2.1, 2.01, 2.001, and so forth. And if I get closer and closer to 2 from this direction, we should see that I'm getting closer and closer to 4. So this is equal to 4. Then I want to evaluate the other side limit. So limit as x goes to 3 from the right, and of g of f of x. And what we see here is that if I get closer and closer to 3 from this side, right, so now I'm going closer and closer to 3, we should see that I'm getting closer and closer to 2 along y, but again from above 2. So these inner values, these f of x values over here, these f of x values over here are going to be, let's say you have 2.1 and then 2.01 and then 2.001 and so forth and so forth. And that's still from above 2. So from above 2 is over here again, and you're getting closer and closer to 2 from above 2, and you get 4 again. So the left hand limit equals the right hand limit, and we have that this is equal to 4. Now I'm going to do another example. I'm going to call it B star, okay, just to say. And I'm going to change up the way it is that F looks. So let's change up the way F looks slightly, and let's see if I can do this. Okay, well, okay, let's see if I could just change this here. Okay, so I'm going to change the way F looks slightly and see how that changes our answer. So let's say now F is the blue line. Okay, let's say F looks like this now. So this is F. Forget about the black part. Okay, and let's investigate the same question. Let's investigate limit as x goes to 3 of g of f of x. And again, limit as x goes to 3 from the left of g of f of x. And let's investigate limit as x goes to 3 from the right of g of f of x. And let's see what we get in this case. So in this case, if you look, right, f is this blue line. As I get closer and closer to 3 from the left, I'm getting closer and closer to 3. I'm getting closer and closer to 2 along y, but from below 2. So now these inner values right here are going 1.9, 1.99, 1.999, and so forth. And I'm getting closer and closer to 2, but it's from below 2. And then if I get closer and closer to 3 from the left over here, or from the right, sorry, from the right over here in this one, I have it that I'm also getting closer and closer to 2, but from below 2 again as well. So these inner values, these x values for g, are going 1.9, 1.99, 1.999, and so forth. And if you look, so these x values for g are coming closer and closer to 2, but from the left of 2, from below 2. So that means that I'm going to be over here. And if we look, as I get closer and closer to 2 for g, as I get closer and closer to 2 along x from the left for g, I get closer and closer to -1. And that's true in this case. It's -1 over here. And then over here, again, these values on the inside are getting closer and closer to 2, but from below 2, so it's approaching 2 from the same direction, and I'm getting closer and closer to -1. Now, the last contrasting example that we could have for f would be something that looks maybe like this. Here, let's see if I can make it look a little bit better. I think I can. Okay, good. So now let's say I have another possibility for f is that it looks like this. So now imagine f being the orange. And let's again investigate the same question. Let's say b, I don't know, b hat. Okay, so we ask the same question, limit with just different possibilities for what f will look like. So forget about f being anything other but the orange. So now f is the orange curve. So limit as x goes to 3 of g of f. Oh, sorry, g of f of x. And again, let's investigate limit as x goes to 3 from the left. And then let's look at limit as x goes to 3 from the right. Okay, and let's see what happens now in this case. So if I look here, right, as I get closer and closer to 3 along x, so here's 3 along x, right? If we look, the y values are getting closer and closer to 2, but from below 2. And this is key, right? That we have it that it's going 1.9, these inner values, 1.99, 1.999, okay, and that's fine, and then we can see what happens. But if we look over here at from the right of 3, so over here, right, f is getting closer and closer to 2 again, but from above 2. So these values on the inside are going to be like 2.1, 2.01, and so forth, 2.001. Okay, and those are the inner values. Now, if I go back to this limit, as I get closer and closer to 3 over here, right, I'm getting closer and closer to 2, but from below 2. So these are x values now that I investigate with g. So I'm getting closer and closer to 2 along x, but from below 2. So I'm over here, and I'm getting closer and closer to 2. If we look, the y values are getting closer and closer to -1. If we look over here, I'm getting closer and closer to 2 on the inside. These values on the inside, these x values, are over here. They're getting closer and closer to 2, but from above 2. And as I get closer and closer to 2 from the other side for g, I get closer and closer to 4. And in this case, I use the fact that the left-hand limit does not equal the right-hand limit, then the limit does not exist. The left-hand limit equals -1, and the right-hand limit equals +4. So this limit as a whole does not exist. And then that is it. Find a function, they call it k of x, and they have k of x defined there in terms of f of x and g of x. They want to know whether this function k is continuous at 2 and if it's continuous at 4. No. What is absolutely necessary to do this is that we need a definition of continuity. So we need to say, when is it that a function is continuous? Let's write it somewhere on the side, way on the sides. So we have definition. Okay. A function is continuous at a if the limit as x approaches a of f of x, or whatever function we're talking about. In this case, let's write k of x since our function name is k of x. So the limit as x approaches a of k of x is equal to k of a. And in this case, we have it where a is 2, and then we're going to change it. We're going to do another part where a is 4. So I want to determine whether or not, basically, in my particular case, I want to determine if the limit of x going to 2 of k of x is equal to k of 2. Now, this left-hand part involves two things. I want to determine if the limit exists at all. So I evaluate the left-hand limit. I want to approach, this function right here on the inside is k of x. I just substituted how they defined k of x. And I want to evaluate the right-hand limit, and I want to see if these two limits are equal. If they're not, then I know that this does not exist, which it means it cannot equal k of 2, which means that it cannot be continuous at 2. Okay, so if this doesn't exist, they can't equal anything, and this equality won't be true. This here, again, means if this equality is true, then k is continuous at a. If k is continuous at a, then this equality is true. Okay, that's the definition of continuity, of continuous. Alright, now to do this, again, I'm trying to determine whether this function that they gave me is continuous at 2. So I need to evaluate the limit as x goes to 2 of k of x. Now that's me, I'm starting that right here. Okay, why am I starting that? Because I'm evaluating the left-hand limit and the right-hand limit. Now, k of 2, I could find out what it is, but I don't even think it's going to be relevant. I don't think it's going to be very necessary, but I want it to equal this here. Let's see what we get when we evaluate the left-hand limit and the right-hand limit. Now, to do this, okay, you want to use your limit laws in both cases, and I'm going to do from the left hand and from the right hand simultaneously. The first thing that you should notice is that this is a product, and that means that we could split it along that product. So it's the limit as x goes to 2 from the left in this case of 4 minus f of x times the limit as x goes to 2 from the left of g of x. And then I split the limit again, and I split it along here, so it's limit, or better yet, sorry, so the limit of a constant is always just the constant, so it's 4, right? The limit of a constant, limit, or better yet, the limit of a sum, the limit as x goes to a of, let's say, I don't know, any two functions, right? H of x plus g of x, whatever, is equal to the respective limits, so it's the sum of the respective limits, so it's limit as x goes to a of h of x plus the limit as x goes to a of g of x. Okay, that's, you can always split it along a sum, right? Now let's see, so up here, right, it would be the limit as x goes to 2 of 4 minus the limit, and along a subtraction as well, this can be split. So it would be the limit as x goes to 2 from the left of 4, and the limit of a constant, the limit as x goes to a of a constant is always just the constant. Okay, for c, k, whatever you want to call the constant. So over here I have the limit as x goes to 2 from the left of 4, which is just 4, minus the limit as x goes to 2 from the left of f of x times the limit as x goes to 2 from the left of g of x. And we should see here that this expression will hold equally true for the right-hand limit. So this over here is one side, let's say. This is the, I'm coming to 2 from the left. And then this will also simplify in a similar manner to 4 minus limit as x goes to 2, because I didn't do anything with these graphs yet. X goes to 2 from the right this time of f of x times the limit as x goes to 2 from the right of g of x. And basically what you have here is now let's actually use these graphs. So what's the limit as x goes to 2 from the left of f of x? We need to be able to investigate what this is, and we need to be able to investigate what this is. So the limit as x goes to 2 from the left of 2. So I'm getting closer and closer to 2, but from the left, from beneath 2 of f of x. This is the graph of f. I get closer and closer to 4. So this is 4 minus 4 over here. So we get 4 minus 4 times, and let's just practice, because this is going to be 0. So 0 times whatever this is going to be 0. But let's just practice. The limit as x gets closer and closer to 2 from the left along g. So this is to the left of 2, so I'm getting closer and closer to 2. The y value is getting closer and closer to -1. And I'm going to get 0 times the -1. The left-hand limit equals 0. Now let's check out the right-hand limit. The right-hand limit is going to be, as I get closer and closer to 2 from the right of f of x, I need to investigate this one, is going to be, well, again, 4. So it's 4 minus 4. And then, if I go closer and closer over here, let's see, as I get closer and closer to 2, from the other side, I'm getting closer and closer to 4 along G. So now I'm getting closer and closer to 2 from the right. I'm getting closer and closer to 4. So I get 4 minus 4, which is 0, and then 0 times 4 is 0. So I actually do need to determine now k of 2, because this limit does indeed exist as a whole. So the limit as x goes to 2 of k of x is 0. Now, does that equal k of 2? So k of 2, right? We have k of x defined here. So k of 2 is just if I plugged in 2 for x. So I get 4 minus f of 2, all of that, times g of 2. And let's see what we get when we do this. So f of 2, if I go over here, f of 2 is 4. So I'm going to get 4 minus 4 times g of 2 is 4. And I get 4 minus 4 is 0. 0 times 4 is indeed 0. And I get k of 2 is 0. So I have this left hand, the limit. I have this left-hand side of the equality, I have the left-hand side of the equality being 0, because the left-hand limit equaled the right-hand limit as 0. And if the left-hand limit equals the right-hand limit, then the limit itself equals that value, which is in this case 0. So I have the limit as x goes to 2 equaling 0, and I just found out that k of 2 equals 0. So what did I find out? I found out that this equality is true. I found out that the limit as x goes to 2 of k of x equals k of 2. Therefore, k is continuous at x equals 2. And you can make it very clear. K is continuous at, I meant to put continuous here, continuous at x equals 2 since, and you could write the definition of the limit, the definition of continuity, I apologize, which is limit as x goes to 2 of k of x, I found out equals k of 2. So it is true that k is continuous at x equals 2, since this equality is indeed true. It's whether k is continuous at 4, right? We want to remember definition of continuity means limit as x goes to a of k of x, let's use the letter that they're using here, it doesn't matter, k of x, the function, is equal to k of a. Now in my new case, I'm investigating whether it's continuous at x equals 4. I have limit, I want to find out, is it true? The limit as x goes to 4 of k of x, this is the question mark, this is what I want to find out, whether it's equal to k of 4. And in order for this equality to be true, this limit first has to exist. So you first got to analyze what this limit actually equals. So what I'm going to do is I'm going to write it as, I'm going to determine the left-hand limit and the right-hand limit. The limit as x goes to 4 from the left of k of x. And I'm going to write the definition of k of x. 4 minus f of x times g of x. And I'm wondering whether this is going to be equal to the limit as x goes to 4 from the right-hand limit, 4 minus f of x times g of x. Now, basically, again, you want to be sure that you know how to use the laws of limits. What this will simplify to after you use your laws of limits, right? You would break it down into a product. You'd say the limit as x goes to 4 from the left of 4 minus f of x times the limit as x goes to 4 from the left of g of x. And then you would simplify that left factor of that product. You'd simplify this part. And you would get something like what we had in the last problem, which was 4 minus the limit as x goes to 4 from the left of f of x, all of that times the limit as x goes to 4 from the left of g of x. And you'd get something else, you get something similar for the limit in the other direction. You'd get 4 minus the limit as x goes to 4 from the right of f of x times the limit as x goes to 4 from the right of g of x. And now we just need to investigate what this is and what this is. And we can find out what the left-hand limit equals, and we want to see if it equals the right-hand limit. Because again, I'm trying to determine the limit as a whole. And if the left-hand limit doesn't equal the right-hand limit, the limit doesn't exist. So let's see what happens in this case. So the limit as x goes to 4 from the left of f of x. So this is 4 along x. I'm coming to 4 from the left. So I'm getting closer and closer to 3. So this is going to be 4 minus 3 in here times the limit as x goes to 4 from the left of g of x. So this is 4 along x. I'm getting closer and closer from the left. As I get closer and closer to the left, I'm getting closer and closer to 1 for g. So this is 4 minus 3 is 1. 1 times 1. And I have the value for the left-hand limit equals 1. Now let's look at the right-hand limit. So what is the value of the limit as x approaches 4 from the right of f of x? So from the right of 4 is over here. And I get that it's getting closer and closer to 3. So this is 4 minus 3 times whatever this is. So what's this? This is 4, and I'm getting closer and closer to 4 along x, and if I go up, I'm getting closer and closer to 4 along y as I approach 4 from the right. So this is going to be times 4. And then this is going to equal, we should see, 4 minus 3 is 1. 1 times 4 is 4. And I got that the right-hand limit, as I get closer and closer to 4 from the right, does not equal the limit as I get closer and closer to 4 from the left. So the left-hand limit does not equal the right-hand limit. That means that this right here does not exist. And if the limit does not exist, it cannot equal anything. Does not equal anything ever. So it cannot equal 4 and k of 4, which means that x or k of x, or k, they just say k. So we also want to justify our answer. So we want to write this last sentence. We want to be able to say why it's true. So I have, so I have k is discontinuous at x equals 4 since limit as x goes to 4 of k of x does not exist And therefore, and you could put these 3 dots for therefore to really show you understand, the limit as x goes to 4 of k of x does not equal k of 4. Asking what type of discontinuity does f have at x equals 1. So there's 3 types of discontinuity. There's this type of discontinuity where it's just a hole. I would rather it be called a hole discontinuity, but basically the limit exists, right? The left-hand limit equals the right-hand limit. They're both tending towards the same value along y. So the limit exists, but f of 1 does not exist at that same value. F of 1 either does not exist, in this case it's not defined, right? It does not exist, or it's somewhere like right here, and in which case you would have that it's not continuous at 1 because f of 1 would be 1, but the limit as x goes to 1 would be something along here, which is what we're going to find out. And in that case, when we have that hole discontinuity, it's called a removable continuity. So that's your answer for the first one, removable discontinuity. Now, the other thing that you would have here is that you could have, this is the correct answer, but you could also have what's called a jump discontinuity. So if you look at G, you have a jump discontinuity here. You have to actually like jump to move here. So this is a jump discontinuity at 2. G has a jump discontinuity at 2, just to go through the different types of discontinuity. And then the last one isn't shown here, which is like something like this. Like you have an infinity discontinuity. Let's say that this is some function. This is a third function, I don't know, h of x, right? Just to go through the different types of discontinuity. And then let's say that, I don't know, let's say that this is, I don't know, 3, right? H of x would have an infinity discontinuity because they're both tending towards infinity. It could look like that going down, where this wouldn't be here, right? They both could be going down. That's an infinity discontinuity. So those are the 3 types of discontinuity. In this case, you have a removable discontinuity. Now it asks for what is a reasonable estimate for the limit as x goes to 1 of f of x. So that's fairly simple from this table. What we have here is that we're getting closer and closer to 1 from the left over here, and we're getting closer and closer to 1 from the right. And it follows along closely with what the graph is illustrating. These values are close to 2.7 over here as I get closer and closer to 1.999, and so forth. Okay, now the value for what this, essentially it's asking what's this value, what's a good estimate for this value right here. And it's basically you just average these 2 points together. You know, because this is just to the right of 1, or sorry, just to the left of 1, and then this is just to the right of 1. And then you can see that this, you know, this 0.999 value right here is like right here. That's, you know, that's 2.784, and then just to the right of 1 is, let's say, this value right here, which is whatever, 2.787. And basically you just average these two, find the middle point. The middle point between them, I could do it as in that it's 0.003 between them, which is 1.5, right? So I would just add this to the lower one, and then that would be the middle between these 2 points. Or you could just add them together and then divide by 2. It's up to you, but it's just basically the middle between these 2 points. So I don't know, it's going to be 2.784 plus 0.0015. It's going to be 5.58712, and this would be your answer. Okay, give a reason for your answer. You could say the average between the closest values on each side of 1, right? That's what all I did. The average y value, if you want to be more precise, right? The average y value between the closest x values on each side of x equals 1, right? Because we're talking about an x value here. And that's basically, your reasoning, right? The average, these are the closest x values, 1.999, and then that's on one side of 1, the other side of 1, closest to it, is 1.001. So then therefore it makes sense that if I'm looking for a y value that's going to be, this y value right here between the two, I take the average between the two y values, and that gives me roughly what this value should be at exactly 1, the limit, what it's getting closer and closer to on each side.